If your network were a symphony, would you hear when a single instrument started playing out of tune? Traditional tools might catch the loud mistakes, like the trumpet blaring the wrong note. But what about the subtle ones? The violin drifting off key in the background, or the drummer speeding up the tempo ever so slightly. Well, that's where graph based anomaly detection steps in, like a master conductor with perfect pitch. It doesn't just listen to each note, it hears how they all connect. And today, for the premiere of Plixer's Tech Talks, we're diving into how you can go beyond isolated signals and start reading the sheet music of your network, seeing the patterns, the relationships, and the hidden rhythms of your digital ecosystem. I'm Peter, and I'm part of the product marketing team here at Plixer. And let's tune in to a smarter, sharper, and more productive approach to anomaly detection with Plixer data scientist Adam Howarth. How's it going, Adam? And
Good.
by the way, Adam is an evening musician, so I'm curious if the whole music metaphor
No,
worked for the opening.
no, that was good. I like that. I like that analogy quite a bit. Um, my name's Adam Howarth. I work on the data science team here. And for opening this Tech Talk series, I wanted to dive in to one of the more complicated components of our AI engine, the graph-based anomaly detection. I think it's an exciting topic, and I thought it would be fun to drill in a little bit deeper, and get into kind of the mechanics of applying data science to network data. So to start, I just want to kind of cover what the AI engine is. Effectively, we have the ability to stream all of the flow observations that we see on the platform off in a Kafka stream. So as soon as that functionality made it into the platform, we basically had the opportunity to build kind of the ultimate off-board analytics platform. So Scrutinizer, which is the core of Plixer 1, has all of the deterministic algorithms that you'd expect. You know, did something happen? Did it not? Things like scan detections, various brute force um, analytics that it's kind of fixed in any environment where those occur. You're going to be looking for the same signals and the same patterns in the data. As soon as we had the ability to stream the data off, we started thinking about what does non-deterministic analytics look like when applied to the platform. And that's really what kind of birthed the AI engine. So this is effectively what we would do with the ability to move this flow data for analytic purposes. And we'll kind of talk again today. We'll focus specifically on the graph anomaly detection, but as the Tech Talk series progresses, we're going to go ahead and zoom in on each of the individual features and functions of the platform. So again, really high level Kafka streaming. It is a Kafka broker on its own as well. So once AI engine's running in your environment, you can also subscribe to the flow data for any other purposes. If you want to replicate it off to a data lake or have some other internal analytics stack that you want to use, it's available for that. Again, it hosts all of our non-deterministic algorithms. They can be pretty heavy. So where Scrutinizer is doing quite a lot to do data warehousing and again, all the deterministic analytics, this gave us a place where we could have a separate compute base for the really heavy stuff that's going to look at huge volumes of data and be able to ultimately run real-time inference against them. So build models, determine behavioral patterns. In the case we're going to look at today, determine kind of normal topological structures of the network. And then again, apply those models to the real-time data as it streams to us so we can kind of identify an anomalous connection or an anomalous behavior pattern as soon as it comes across the platform.
Yep.
So again,
And
ultimately,
for,
this hosts kind of the other feature set, our forecasting engine, our malware traffic classification trees, encrypted traffic analysis, an intelligent DNS proxy, behavioral anomaly detection, which will be the focus of next week or next month's talk, and then today's focus, the graph-based anomaly detection engine.
and for those of you watching, we're really going to get kind of technical with these, and there's a lot of scorn, if you will, toward very, marketing organizations talking about, oh, it's AI driven. Oh, it's all working with AI. In this series, we're really trying to get into the nuts and bolts and really, really kind of open up the cloak and show you exactly what and how we're using AI to do some of the cool stuff within our technology.
For sure. And to that point, Peter, AI and ML have gotten kind of enjoined over time.
Yeah.
I think now we think of AI kind of a lot more along the lines of like the chatbot LLM space, and that's content that we have coming that we'll focus on a few tech talks from now, around new features on the platform. Um, but for now, what we're going to do is focus on all of the what would have been machine learning, the kind of the traditional ML functions, kind of the really powerful, mathematical modeling that happens to get good results, out of, again, huge volumes of data that's coming to us kind of nonstop all the time. So to start on graphs, kind of at a high level, like why graphs? Why is this something that is an approach that makes sense for IP-fix NetFlow data? So a lot of this thinking is based on this paper, Inductive Representation Learning on Large Graphs. And really the problem that they identified and focused on was in most graph analytics, you need some definition of the entire scope of the graph in order for a lot of these algorithms to run efficiently and well. The issue being is that as data gets larger, and then of course specifically in IPFix and NetFlow type data, we're talking about graphs that are enormous, and the computational complexity of traversing those graphs and doing traditional graph analytics becomes intractable in many cases. So that's kind of half of it, is just the scale of it. And then additionally, the thing that we focus on is the induction of graphs, where the best analogy that I've been able to come up with is when you're in an airplane flying at night and you kind of look out the window, you can get an idea of where all the roads are based on where you see car lights traversing roads. So in your mind, you've basically induced a representation of what that road network would look like based on observations. So very similarly with NetFlow data, we have a stream of IPFix coming in that are observations of things that happened on the network. There is an actual underlying network of things that are physically connected, that it's representing, but ultimately we can only induce a model of what the graph that network represents would be based on observations. So that's where induction comes in. So the model that they built here effectively allows us to develop features that are associated to nodes on the network without needing a complete view of the entire network, as well as the ability to actively adapt to new observations of things that maybe weren't known previously and expand kind of the internal representation of how we understand the overall graph model from these induced subgraphs. So how that applies specifically to our data, this is a debug output image from the back end of the graph anomaly system. And as kind of wiry and complicated as this gets, this is actually pretty low volume, only a few hundred hosts, and a few hundred connections. So visually for us, we can look at it and it looks like a lot of things that you maybe see in nature. We were talking earlier, it looks, kind of like if you're looking up into the stars and how, gravity collects things together. That has a lot to do with the kind of force direction methods that are used to draw graphs. But ultimately, we can look at these and get some intuition as to what the topology underneath it is. However, in practice and on real full production scale networks, these end up looking more like a ball of yarn where the node density is so compact and the edge connections are so dense, in the sense that there's a lot of nodes in your network that are fully connected, things that talk to a lot of other nodes, that visual representations start to kind of break down. And being able to just quickly look at something, the kind of human layer falls apart a bit. So what I always try and think about when we're looking for places that make sense to apply machine learning and AI are really those volume scenarios where it's, how could an individual actually process some load of data? So that's where graph-based anomaly detection comes in. Is it algorithmically and using kind of the inductive representation principles of that paper can take these large graphs that otherwise no individual would really be able to make sense of and still consider every edge, and every node that's present in the graph at the same time.
Yeah, we talked about how it looked like, a shot from Hubble. It also reminds me of, they always have these helicopter shots during the 4th of July over Los Angeles, and that totally looks like all the illegal fireworks that are being shot over the
Oh,
city on Halloween.
yeah. Yeah, a lot of it just comes from the symmetry of graphs. A lot of times you'll see like almost like dandelion looking structures,
Yeah, it's
specifically
pretty
in
cool.
networks where you have one device that talks to many things over a particular service or port or protocol.
Yeah.
Um, and it's just kind of a one layer deep connection. But yeah, but again, so it's very easy for us to visually kind of make sense of these when they're low complexity graphs, but as the complexity goes up, it just becomes something that, is kind of a machine speed problem. And then further, to do this in real time as new edges are popping into the graph, at 100,000 flows a second or higher, you really need some sort of kind of analytic tool that can adapt and keep up with that flow rate.
And you were talking kind of looks like yarn. And what you mean is that each of those little tiny dots, right, have at least some sort of line or connector to some other node within the network, right?
Correct. Yeah, and just at full production volumes, you basically run into like a pixel issue where the actual image that's being rendered out that represents the graph is less granular than
Yeah.
how many connections are there. So kind of the whole visual process breaks down altogether. So while it's a great model for thinking about graphs, in practice they're just so dense that it doesn't really hold up in a way where we could manually do any sort of review. So again, kind
Right.
of leads to where it makes sense to turn into a machine learning problem.
Yep.
So this whole process starts as flow data comes in. We look at every node and its series of connections over a period, a time aggregation. So at the lowest end, that's every minute of flow data that comes in. That's kind of trickles all the way back to how flow caches aggregate data on the actual devices that are exporting this information to the platform. And then it aggregates up into higher time frames, 5 to 10 minutes, in order to just get a better induced subgraph that's more representative of any point in time on the network. So these features are developed from taking that aggregation per host. We have a port binning strategy. So if you think about the port range between 0 and all the way up through the ephemeral end of it, it's skewed a bit just to give more importance to well-known ports and lower-level ports that require elevated access to use. Um, Registered ports in the middle are kind of known applications. Then ultimately, our dynamic and ephemeral is really just kind of the random space of ports off in the, again, ephemeral side of a connection. So every conversation that comes through, each node that's observed or each host or network interface has a feature vector associated to it that's derived from basically this histogram of port binning and the packet density that's used on each of those ports for that host. So it gives us a way of kind of fingerprinting each individual host in a way that helps us get into the model that paper uses, where the nodes need some sort of representation. So this is kind of at the lowest level. So if you think, you have a host that's just doing SMB traffic, HTTPS, basic web, and DNS to kind of feed that basic web traffic, it creates a feature vector based off just that host's conversations that will be somewhat unique to how it behaves on the network. And when we get back into thinking about the graph sage model, which is that paper for induction, they basically face the idea that if you have an unbound graph in size, you cannot use a traditional breadth first or depth first search because you don't know kind of the cardinality of what any of those steps will be. So that paper suggests a model called graph sage, which is graph sample and aggregate. And effectively what that allows us to do is select a sample neighborhood for each host. In our case, it's a 2-level neighborhood. That's the example the paper's based off, and that seems to be what people get the best kind of results with. So every node has its neighbors and its neighbors' neighbors considered. And then the feature vectors that we kind of talk about in this previous slide, where every single entity on the network has its unique feature vector like this, gets aggregated down through a graph convolutional model. Convolutional models, that those words kind of got thrown around a lot during like the real deep learning surge. The best way to think of a convolution is if you're blurring an image, that's a convolutional operation. It's a Gaussian convolutional operation. So if you almost think about having Photoshop open and dragging like a blur tool across, that little sample of the photo that it's taking, it's going to grab some average or some Gaussian based on the pixel data that's within your cursor that's selecting, and then ultimately just republish those pixels to whatever that average value is, and it gives you that kind of blurring effect. So whenever you hear convolution, that's really all you're talking about. You can think of it very much like dragging a blurring tool across an image and kind of what the math might look like in order to blur that in. So when we talk about graph convolutions, we're talking about navigating a graph, and rather than in an image where its neighbors are literally the pixels that are above and to the right and below, in a graph, it's what are you connected to over known edges. So in the first stage, we take some samples from our first layer of depth and our second layer of depth. In the second stage, the individual features that were the fingerprints that were developed for all of those nodes are run through a graph convolutional model to build an aggregate that basically informs the relationship of that neighborhood using the individual fingerprints of all the participants in that neighborhood. Those, as part of the graph convolution, are brought back into the individual host at the center of this that you're talking about. So this is done for every host. We're just talking about one specific, pass at the moment. So the aggregations are brought back in from that second layer to the individual host, and then it redefines the feature for that individual host. So if we think about this guy in the middle, and he has, some definition based around his usage, and then there's a certain subset of hosts on the network that are within, one hop or one direct connection from the host. They'll all have their own unique definition. And then we go out one step further to a sample of the hosts that first neighborhood talked to, and that ultimately develops our kind of immediate neighborhood and our secondary neighborhood. So each individual node on the graph goes from originally being represented by its own, that again, the histogram of port usage, to being an aggregate of both its neighbors and its neighbors' histograms of port usage. So now the individual host at the center of this is no longer defined by its own behavior only, but defined by its behavior influenced by the behavior of those things it talks to on the network.
Yeah. With it, yeah. So kind of takes up sort of the neighborhood's qualities, and then your local township, if you will, or just the kind of side streets that are contained around your neighborhood here. I'm just sort of thinking of my own neighborhood and envisioning how the roads are out there, past our street sign.
Exactly, right. So you start at your locality, and then there's some very specific definition of how that's used. And then one step out from it, there's going to be some, fairly common features that you'd associate with that neighborhood just based on kind of the intent of networks in the first place. And then ultimately, as you get to the second stage, you find another kind of general feature quality. And then ultimately, the graph convolutional network, through looking at all this data, learns a way of just cooking all of that data down into a single representation for the initial locality we were talking about, to better, again, just set it. Not only, there's lots of the original example, there's lots of PCs that are going to do SMB and browse the internet and use DNS, right? But there's going to be only very specific ones that then are situated in, this 2 layers of locality. And again, all of the behavior that gets brought in from the nodes in that part of the network too.
Yeah.
So ultimately,
and then obviously, I know, I mean, you haven't really gotten to it, but just kind of tease out when an anomaly happens or an anomaly is detected, you can now know at least that general neighborhood and area, right? To then investigate what the relationships
correct.
are with that specific anomaly that got detected.
For sure. Yeah, that will come up in a bit. But really that is what the end goal here is not
Yeah.
only identifying a connection on the network that's just generally anomalous, right? But a connection on the network that's generally anomalous set in the context of the subgraph that was induced and it was observed
Hmm.
in. So it goes a little bit beyond just kind of a standard situation where, it's odd that these two hosts communicated, over a certain important protocol, and further extends it to it's specifically odd that these two hosts communicated over this important protocol, given the fact that the normal behavior that's observed in both of their localities doesn't suggest that this is a connection that would happen,
Yep. Yeah.
probabilistically.
The out of the ordinary.
So ultimately, what that does is once the graph convolutional pass happens, it turns our stream of flow records that we see basically into a series of pairs where we have this embedded feature definition now that again is not just itself, but the entire locality that was cooked into it, connecting to another host that has its entire locality connected into it. So it transforms kind of an initial, very basic feature description that's purely based on what was observed in flow data and transforms it into this space where the hosts are again set into the graph, um, based on the observations of other hosts around it. So now the stream of conversations is really looking at those two feature vectors compared and how likely it is that two feature vectors like that would have a connection between them. So if we grab
Mm.
just one of these, we have our source node on the left and our destination node on the right. They have their aggregate representations. We take both of those and composite them together, and it makes basically a feature vector that's twice as long. And that composite feature vector is now unique specifically to this conversation. Again, going kind of unwinding it all the way back, it's that source node operating in its locality on the graph and that destination node operating in its own locality on the graph have formed a connection. How likely is it that two feature vectors that look like that would have actually made a connection in your graph?
Hmm.
So on the back end, again, every minute there's an aggregate of graph that's happening, again, an induced subgraph. And then every 5 or 10 minutes, there's a aggregate induced subgraph. And what that allows us to do is then generate negative pairings. So now that we have these induced, um, or not induced, but aggregated representations for the nodes, we can actually go through it and figure out which connections do not occur naturally versus which connections do occur. The ones that occur are kind of implicit in the fact that they were observed. So what that allows is we can then train just a binary cross entropy standard MLP. So just kind of if you think of like the most generic kind of neural network example you've maybe seen, that's all MLP is, multi-layer perceptron. It's just a funny word for neural network otherwise. And what that allows us to do is where it's just a binary classification of is this a connection that should or shouldn't exist given what we've seen, and given the subgraphs we've induced from your network. We can train this model up on pairs that were observed. And again, the negative examples where the two feature vectors never formed a connection. And then that composite is basically put into the first layer of this neural network. And then the output is effectively a score as to how likely it is that that connection belongs on the network. So
Mm.
again, I'm unwinding it all the way back to the beginning. We've built in kind of the initial observed features of the host. Those are enhanced with those same initial observed features of all the hosts in its general locality. Those create these aggregates. Then on new pairs that we see, we can bring those aggregates in, composite them together, feed them into an MLP, and then ultimately get a classification as to whether or not it's likely that conversation should or should not have occurred on the network. So that's really kind of the whole stack of how the graph-based anomaly detection works. Ultimately, the MLP models are cycled and circulated on the back end to keep them kind of current with the data that's being observed. It's very
Mhm.
unlikely, these graphs, you could train one of these graph detectors and then just have it sit in place for months at a time. It's pretty unlikely that your overall network topology is that stationary. Um, that would, that representation would be meaningful over a long period of time given business dynamics, et cetera. So at any point in time, there's a model being trained in the background, there's a model being run as inference, and they all overlap a little bit as well. So that way, there's kind of no break in between those, and you always have an active model that's running inference for you. There's always a model that's being trained up. And these are all partitioned by weekday and hour. And then when inference is run, we actually run inference against the current hour, the previous hour, the next hour, and then that's done for the previous day and the next day as well. So you end up getting this nice general score of both if this connection was likely to occur at the moment, as well as if this connection, if there's, there could be some temporal deviation, right? Some behavior that is expected happened a little sooner, a little later, for whatever reason, shifted a day, but it's still ultimately relation that we expect to be normal on the graph.
Yeah. Boy, I couldn't imagine a human trying to manually figure all this out.
It just changes too frequently is really
Yeah.
the main issue. Is you could go through and do all of the work to get some sort of manual analytic pipeline to review it,
Yeah.
but then
Network
ultimately
map.
in the process of doing that, it's, like 100 billion flows have passed you also.
Yeah.
So
Right. Right.
um, it's really one of those things where it's just the speed of ingestion around IPFix and NetFlow is where this becomes so important. And again, being able to run inference in real time against extremely high flow volumes is something we've spent a lot of time on, making performant and be able to keep up. Because again, your network never really stops, so it's not like you can defer maintenance or anything like that. You need to be able to have these models constantly evaluating new connections all the time and constantly training new models again for this kind of always online situation where we've got models training in the background that will be swapped into inference. Um, it's just kind of this constant process and constant maintenance of graph representations, and an understanding of, again, what these composite feature vectors look like and should look like on your network further.
Is there a typical time frame? I had one of those, cool words, but a typical time frame where the training goes then, upgrade, not upgraded, but put into inference, or it's up to the customer to decide how often they want to,
Yeah.
go to the new model, go to the new model. Or is it something that's kind of automated based on what the model's finding?
Yeah, so it is configurable. The default behavior is basically on a weekly schedule.
Oh,
So
okay.
yeah, so each week, effectively, you turn it on for the first week. It just needs to learn. Otherwise, it's just guessing. If it's seen no data, and it's going to go run
Yeah.
inference. So for a week, it learns. As soon as that model basically starts passing some tests against known connections, because that's really where the benefit comes from, is that we have a stream of connections that do happen regularly on the network, and that's really what aggregating longer time periods of network behavior help with. Is it gives a way of um, sifting through things that are very unique connections but maybe normal, and then things that are very generic connections for that network and happen regularly and all the time. So there's some internal validation mechanisms that basically qualify the model to be put into inference. And then as soon as it meets that standard, it gets pushed up in inference and then starts serving alarms against the front end. The outcome of this basically distills down to just an alarm in the alarm view of Scrutinizer, that highlights these suspicious connections and then offers some pivots into kind of looking at, the surrounding data that supports the context of what was going on for that individual host at the time. It made a connection that the graph engine found to be anomalous.
Yeah, it helps you chase down the instance.
So awesome. So next time on May 6th, we're going to focus on the behavioral analytic engine. It is kind of the other dimension to graphs. So if graphs are looking at the topology at any kind of freeze frame in time of the network, behavior is going to look across time and how every individual node and network interface typically uses its port and protocol services temporally, and then ultimately distills out a few different classes of behavior that are known for every participant in the network, and gives us an opportunity to identify instances where a node on the network is behaving in a way that is not something that belongs to a known class. So that
Yeah.
will be the next tech talk and the next kind of feature of the AI engine that we'll focus on.
You know, we were talking when we were preparing for this a couple weeks ago that I know there's got to be somebody out there that's going, oh no, the graph AI that kind of misses this or it doesn't do that. It's perfect for a lot of things and it's a great tool to use. However, there may be other instances like our next tech talk that maybe fill in the gaps a bit.
Yeah, and that's it kind of leans into why the AI engine is structured the way it is that it's almost you can think of it like senses. There's several different senses that it has
Yeah.
where it models and can detect things very specific to how that data is ingested and modeled. But in the case again, graphs are very instantaneous and kind of what we're currently inducing off real-time data and really looking at topological inconsistencies, whereas behavior thinks over time. It basically looks at temporal vectors of how all of those
Right.
things are working. So that's really the goal of the AI engine in total is making sure we have kind of any weakness of an individual algorithm. There's another algorithm that kind of
Right.
covers the basis for making sure there's a total analytic solution around monitoring these things.
Right. Right. Cool. So May 6th, we'll put some information out there for our next tech talk. And we're also going to be at Cisco Live June 8th through the 12th at the San Diego. It's at the convention center, right? The convention hall there in San Diego, booth 1940. I believe we'll both be there. So hopefully you folks can come by, although we'll have our next tech talk a month before the Cisco Live, but we just want to make sure you folks know that we'll be at the Cisco Live conference to come visit us there.
All right,
Do
so
we
that
have a
concludes
closer? That's
kind
a
of our initial
closer.
tech talk here. So thank you everyone for joining us. I appreciate it. If you're actively a user of the product, feel free to reach out to tech services and we can kind of do some training in context with your data, your environment, etc. If you're new to
Yep.
the platform, also feel free obviously to reach out and we can figure out how these various things would apply and get value from your environment.
And if there's something within the product that you'd like us to potentially investigate on Tech Talks, if you have a feature or an item that you want us to maybe dig into, give a little more insight, we're certainly happy to do that too. Right, Adam?
Yeah, for sure. Any suggestions are greatly welcome.
Perfect. Cool.
So.
There you have it for our first tech talk. I hope you all enjoy it. Please share with the like-minded folks. We'll be coming at you every month. Thanks for your time, Adam. That was really interesting stuff.
Yeah, thank
Fascinating.
you. Thank you very much, Peter, and thank you everyone for joining.
Yep. For my good pal Adam, I'm Peter, and we're with Plixer. Thanks for watching.